This lesson is from Unit 8, Lesson 4, Oblique Triangles and the Law of Sines. An oblique triangle is defined as a triangle without any right angles. The first half of this unit was devoted to solving trig equations based on right triangles. In the real world, we're going to come up against triangles that are not right triangles. There are two laws. Today we'll start with the law of sines. If you recall in the last lesson, especially problems like the baseball stadium, we would often set up two separate right triangles. We would solve each one of those trig equations for a given variable, such as h, and then we would solve the resulting equation. If you look at the proof located in the top half of your notes, this proof shows where the law of sines actually comes from. We have a left triangle and a right triangle. Both were set up with trig equations involving sine. Each of those equations were solved for the variable h. Substitution was used, and it left us with a proportion. It turns out that that proportion can be extended not just to talk about sides A, B, and angles A and B, but also side C and angle C. Here's what's important from the law of sines. In order to set up a proportion which only has two fractions, you must have one opposite pair. You must know the length of one side and its opposite angle. Now, there are two cases that we can actually explore using the law of sines. We can use angle side angle or angle angle side. When you have either of those two cases, the law of sines is very straightforward. You'll see in part 2 of the lesson that if we have what's called the ambiguous case, we're going to actually have to verify our solutions and check to see if there are any other triangles that may work. In this case, that would be when we had the length of a side, the next side, and then the corresponding angle that follows. In example 1, take a moment to read. If we set up a diagram, it'll be similar to the one on the right. This is all of the given information. Notice, we have angle B and side B. This is our opposite pair, which signifies we should use the law of sines. By setting up our proportion, fraction equal to fraction, we can substitute in the information. We would then cross multiply and solve our equation for C, which is the length of the side opposite angle 100. In this case, using our calculator correctly, especially with parentheses, C has a length of 34.95. I would advise verifying this, making sure that your calculator does in fact give you this answer. Now, using the 180 rule of the triangle, we can find the other angle, which is 55 degrees. We then can use the law of sines again. I would recommend using the same fraction of 15 over sine of 25 because that was given to us in the given information. Set up a second proportion. Instead of solving for side C, we're now going to solve for side A, which is located across from the 55-degree angle. Cross multiply, solve for A, use your calculator in parentheses correctly. Your final answer is 29.1. Example 2. Based off the given information, a drawing similar to the one to the right can be drawn. Note, in the given information, we have an opposite pair. We have angle A and side A that are given to us. This signifies we should use the law of sines. Set up our first proportion. Again, the law of sines does have three fractions, but at any time we only use two of them. We set up our two fractions, we cross multiply, and then we solve. What makes this problem different is the fact that we're now solving for angle B. When we solve for angle B, just like earlier in the unit when we were solving the trig equations, we have to use the inverse functions of sine, cosine, or tangent. If we do this correctly, we find that angle B is 17.4 degrees. Once we know that angle, we can use the 180 rule to find the third angle, and again use the law of sines to solve for the unknown side. In this case, the unknown side is 9.3. Take a moment to read example 3. Pause the video if needed. The hardest part of example 3 is drawing a picture that represents the given information. Some of you struggled with this in the last section. You need to practice these problems. On the test, you will not have any problems that do not correspond back to one of the other word problems in the unit. We have a pole that tilts toward the sun at an 8-degree angle from vertical. The dotted line represents vertical, the star represents the sun. That pole casts a 22-foot shadow. The angle of elevation to the top of the pole is 43 degrees. We're going to assume that from the subject of the previous sentence, we were talking about the pole tilting toward the sun. The angle of elevation to the sun is the same as the angle of elevation from the end of the shadow. In this case, it's 43 degrees. We also can fill in the fact that we're trying to solve for how tall the pole is, x. Now, what we need to do is recognize if vertical is straight up, which is 90 degrees, then this total angle is 98 degrees. If we focus on the oblique triangle made by the outermost lengths or segments, we can then solve for the third angle, which is 39 degrees. This is to our advantage because now we have the opposite pair of 22 as a length and 39 degrees as the measure of the angle. We can set up our equation, cross multiply, and solve for x. Again, drawing the problem correctly is the hardest part.